Hello, this is Brad Grand at WDTD. This is a recorded webinar from the summer of 2018 on mesoanalysis and severe weather warning operations. I'm going to propose two cases to illustrate the role of mesoanalysis in severe weather warning operations and pose some questions to you. And it'll be about 30 minutes or so. So without further ado, we'll get started. Here's the problem. It's 2 p.m. on a holiday weekend in the winter in the southeast. You're one of 3 warning meteorologists on shift. Your job is to perform the job of severe mesoanalyst by analyzing the mesoscale environment and providing critical, accurate information to the warning forecaster and communicating that threat to media and partners. Case numero uno. Your area of responsibility is highlighted in the blue rectangle. Notice that it encompasses more than one county warning area. That is highlighted by the blue star. And that is an example illustrative of the domain of responsibility. When you analyze mesoscale data, you're looking at data from 2 to 200 kilometers out, so you have to kind of go beyond typical CWA domain. The setup at 1930Z is there's a surface low in southwestern Missouri with a cold front extending southward through northwest Arkansas. There's a stationary front extending eastward across Arkansas into Kentucky, and also another boundary further north in the cooler air, but the stronger deep layer shear is illustrated by the blue vectors are occurring north of that northernmost boundary. In the warm sector south of the stationary front, 0 to 6 kilometer shear or effective bulk shear is on the order of 60 knots. You can see from the visible satellite imagery a large area of widespread clouds and precipitation. Layered cloudiness extends across much of the region. In the warm sector, there are some indications of cellular convection developing. So next I'm going to show you a series of mesoscale plots from SPC starting at 19Z. First one is just a surface plot showing the mean sea level pressure, temperature, and dew point. Standard convention labeling for all these SPC meso page plots. 0 to 1 kilometer shear vector. Notice a very strong maxima back to the west across northwest Arkansas of areas of 50 knots, 0 to 1 kilometer shear. As you go further east, it drops off considerably. ML Cape and MU Sin and effective bulk shear displayed on this product. Significant tornado potential. STP indicates areas greater than 1 extending kind of west of the Mississippi River, West Tennessee, back into Arkansas especially. The further east you go, the values really drop off. LCL height then 0 to 1 kilometer SRH. Again, higher values back to the west, just to the south of the surface low in Arkansas. Observed sounding at Little Rock at 20Z indicates a MU parcel CAPE value of 2266 joules per kilogram with no CAPE. Kind of a tall, skinny CAPE profile. Winds out of the south veering around out of the southwest in mid layers, and you can see a very impressive photograph displayed with a values of effective bulk shear 68 knots. The Sherby parameter shows values generally greater than 1 over much of the mesoscale domain. SureB is a good discriminator for assessing high shear and low cape tornado environments. You can see the box and whiskers chart showing the SureB values for tornadic events, warning, nulls where nothing happened, and then radar where nothing happened. An improvement to the SureB has been developed and is in the MOSH and the MOSHI, and that's available on the SPC Mesoanalysis page. The latest forecast of the HER, valid at 20 and 21Z, shows a few storms kind of popping up over northern Mississippi and western Tennessee, but a large area of clouds of precipitation back to the west and to the north of the stationary front. The HRF showing the 3 hour max 2 to 5 kilometer updraft velocity, ensemble max showing area 30 to 50 across Arkansas into southeast Missouri. Mesoscale discussion issued at 20Z prior to the tornado watch indicates a hatch area of increasing tornado wind threat, with the watch likely across extreme northeast Arkansas, Missouri Boot Hill, and northwest Tennessee and western Kentucky. Mosaic radar kind of shows again large area of showers and thunderstorms ahead of the front, but then when you get further out west, like across the river, just one or two storms kind of starting to develop. Again, dew points have increased to low to mid 60s across this region, and temperatures with some heating now are in the mid to upper 70s, which is impressive for February. Radar at 2136 from the KHPX radar indicating reflectivity, SRM, correlation coefficient, and ZDR in the lower left. Shows storms kind of developing just south of Guthrie to St. Bethlehem and Clarksville. One particular storm showing signs of a little bit of convergent rotation. At 2142, the next volume scan, you can see real strong convergence here at the half-degree slice to the east of Clarksville, with this one cluster that's starting to kind of develop a little bit of an S shape. So question one, what appropriate input do you provide to the warning forecaster as a severe mesoanalyst? Think about that. Next question, a few minutes later, a radar scan at half degree, looking at 2201. That one thunderstorm is now about to cross over into Kentucky from Tennessee, and now has an inflow notch on the leading side, and now showing signs of convergent rotation. Next question, well, your warning forecaster had to step out a minute, so you have to make the warning decision. You've been looking at the environment. You should know and be able to make a good decision. So what's your warning decision? Hopefully you made a wise decision. Finally, role of a severe mesoanalyst is to provide information to your partners as well. So what message do you give your EMs about trends from 22 to 0Z in the eastern part of your CWA? Well, first of all, what happened this event? Large area of wind with several tornado reports across the lower Mississippi River Valley into Tennessee and Kentucky. Two tornadic storms of interest actually traversed across your region during the time period, and one was rated EF2, the one there, the state border crosser northeast of Clarksville, with other touchdowns further east. So a good answer for mesoscale input was discrete storms were going to develop out ahead of the line with a isolated tornado threat and a considerable wind threat, as evidenced by all the blue wind reports. And the EF2 damage east of Clarksville, you can see this tornado really wiped out this house, and unfortunately there was one fatality. So in this case, the severe mesoanalyst can really draw strong evidence supporting evidence to the warning forecaster support tornado warnings. And hopefully that was your decision back there at 2136 and again at 2201. Case number 2. Let's move to the summer, and this is during the climatological severe minimum. Storms are increasing in coverage and intensity, approaching the metro. A severe thunderstorm watch is in effect. There are 2 radar warning meteorologists on duty, and you have been tasked to help with communications and the Mesoanalysis desk. Here's the watch issued and valid till 04Z. Portions of Oklahoma into extreme southeast Kansas. It was a cluster of storms kind of intensifying across northern Oklahoma through Ponca City and south and east of Wichita. And the severe thunderstorm watch indicated primary threats: scattered damaging wind, isolated significant gusts to 80 miles an hour. Possible isolated very large hail events to 2 inches in diameter possible. So the summary of the watch is that their cells and clusters will spread east and southeast with a risk for severe wind and hail. Let's see how this turned out. First of all, let's look at some mesoscale data. First of all, the LAPS 4 panel at 04Z shows SIN, 0 to 1 kilometer SIN, and 0 to 6 kilometer bulk shear vectors and computed CAPE in the upper left. And going clockwise in the upper right, we see 0 to 6 kilometer bulk shear vectors with the 0 to 1 kilometer bulk shear vectors in blue. So the yellow is the 0 to 6 and the blue is 0 to 1. Also we have helicity kind of highlighted in the image color, but the higher values again naturally where you have the strongest shear northwest of the CWA. And then going around, we have LAPS LCL height showing values pretty low and energy helicity index. And then in the lower left, we have the bunkers right moving supercell vectors in magenta and the left moving supercell motion in blue. And then the 0 to 6 kilometer HGL mean wind with the light brown. So overall, shear is increasing. But CAPE is the main driver. Now you can see your area of responsibility now is the TSA kind of warning area, but your mesoscale influence encompasses Oklahoma, Kansas, and then again surrounding areas. So looking at 0 to 3 kilometer bulk shear vectors, since this is kind of a QLCS type of event. Looking at 0 to 1 kilometer most unstable CAPE values greater than 2,000 across the eastern corridor of the CWA and then back to the southwest. And most unstable CAPE 0 to 1 kilometer is just the image. So CAPE and shear together, 2 real strong modulating factors for QLCS intensification. So let's go to the radar at 05Z, 4 panels, looking at Z, ZDR, correlation coefficient, and velocity clockwise in the different quadrants, and then the CWA is highlighted in red. So storms are just increasing and starting to get organized, but nothing severe as of yet. But take note of the orientation, kind of north-south orientation. So it's starting to organize into a linear complex. Dew points are very high out ahead of the storm, and temperatures are very warm. Midnight, still temperatures in the 80s. Behind the complex, temperatures drop way down into the 60s, so there's a very strong cold pool. And it's looking at the velocity, there is some convergence, so there's some deeper updraft structures developing with some of the structures. CAPE and effective shear at 06Z. You can see the biggest CAPE is to the southeast. Drops off quite a bit as you go southeast to northwest. And the effective shear is right around 40 knots. So would that yield supercell structures? Possibly. Observed sounding at 0Z kind of shows this well-mixed boundary layer from 0 to 3 kilometers. And very steep lapse rates. Above that, you've got quite a bit of CAPE. It's over 2,000, and the winds are right out of the south, right up to the LFC, and then it kind of veers around out of the southwest to west. Forecast sounding for 6Z in the vicinity of Tulsa shows again that in kind of inverted V profile below the LFC, very dry mixed adiabatic lapse rate. Above that, you've got quite a bit of cape and winds kind of almost westerly, 30-35 knots. And you can see the height of the freezing level, the -20, -30. So got some buoyancy to deal with. The low-level shear is a thing that we're really monitoring on the mesoscale. This is August, so again, you're not thinking so much about a severe weather outbreak. So the first question, what hazards do you expect in the next hour to move through the Tulsa metro? To help answer that question, let's look at the KINX bad wind profiler data from 0513 to 0615. Time moves from left to right, and so you can see the profile southwesterly to southwest, 10 to 20 knots at about 4Z, but then you get, for the next 2 hours, winds increase generally by 10 to 15 knots. And then as we go forward in time, it really increases, especially as you get into that area from around 0541 to 0615. So right around the 1 a.m. period, we really get an increase in the low-level jet, increasing the wind speeds. And that really has a tremendous influence to the overall strength of the updrafts and the structures of the QLCS. At upper levels, we also see an indication of maybe a rear inflow jet kind of starting to come down from that really strong cold pool. So again, 0 to 9,000 feet, that 3-kilometer layer is really important to monitor. Temperature and dew point and mean sea level pressure at 6Z. Some convergence along that boundary. The main thing is the copious amounts of temperature and low-level moisture that the system has to work with. Effective layer STP is also starting to increase. We didn't really think there was a threat. Only severe thunderstorm watch issued, but things are changing. When you look at a QLCS mesovortex, there's 3 ingredients that need to be in place for intensification for mesovortex genesis. It's the 0 to 3 kilometer line normal bulk shear magnitude greater than or equal to 30 knots. That's highlighted in yellow for this one example conceptual model. You want a balanced or slightly shear dominant region along the line. That's the light blue, and then the dark blue is some area where you have a rear inflow jet or an enhanced outflow causing a surge or bowing structure to kind of realign the updraft downdraft convergence zone, which is highlighted in white. When you get all these 3 areas together, that's when you need to be thinking about QLCS mesovortex development intensification. So the decision point, 0608, we've been watching this. The warning forecasters issued a severe thunderstorm warning, but all of a sudden in the last 30 minutes things are starting to change, and if you look at the updraft downdraft convergence zone, you can see it's starting to kind of curl back to the north along the northern part of the line, north of Collinsville. But then also I want you to look at just south of Tulsa what's going on here and see this little surge. This area is an enhanced rear inflow jet, so right here where the it's kind of balanced from Tulsa up to Collinsville through Owasso, but south of here it's getting a little bit more slightly shear dominant. And so if we think about this, and we've got the bulk shear vector now, it's increased to 40 knots, and line normal, it's almost perpendicular to the line in this region, and up in this in places A, B, and C, where would you expect intensification? So your warning forecaster needs input on the mesoscale. Where would you tell him or her the most likely area for tornado development in the next 20 minutes? It's more than likely going to be A, based on this surge, and also B. So A and B are both likely locations. C, it's you don't really have anything, but anywhere in between here, you don't have the line normal bulk shear greater than 30 knots. You've got it probably it's almost parallel to the orientation of the updraft downdraft convergence zone. So this is kind of a area you're not really too excited about, but this area southeast of Tulsa and then up here north of Collinsville in location B are 2 hot spots. And so what you might do is issue a tornado warning inside the broader severe thunderstorm warning, and kind of highlighted some of the areas where the three ingredients match are coexisting. So in this particular case, it did produce a tornado, EF2, from just in the southeast downtown area, tracked across Highway 169 and then lifted, and then again touched down again east in Broken Arrow. By early Sunday morning, tornadoes had struck Tulsa and Ooltewah, damaged several businesses, residents, injuring approximately 25 people, and many roads were still closed as of Monday morning. And the Weather Service confirmed that an EF2 touched down at 119 just west of I-44 on East 41st Street and traveled 7 miles. So most of the EF2 damage was in this Midtown area near I-44, where several businesses such as this TJ Fridays bit the dust pretty good. And then it lifted and then touched down again, and Broken Arrow created EF1 damage. And just as the Broken Arrow tornado lifted, this one here, a third tornado occurred up in Ooltewah, downing power lines and damaging a residence. So that was the one further north up here along the line. So in summary, important task for the severe mesoanalyst, you need to do kind of three basic things. One is develop a situational awareness of the mesoscale environment before and during potentially impactful severe weather events, and be able to communicate this information to your warning forecaster in the office and also external partners. So they're kind of the conduit for mesoscale information. And you do this by a number of methods, but one is by calibrating model data with observed data, such as VAD1 profile data, as much as possible, because the models can be off, and note trends in buoyancy gradients, boundary identification, low-level wind shear changes, and look at several CAMS runs. Be able to, again, modulate the amount of information to warn or not warn. So just a little bit about mesoscale definitions. We're talking about the nomenclature, typical nomenclature that we're looking at here is mesoscale beta on the dimensions of 20 to 20 kilometers and a time frame of 30 minutes to 6 hours. This is really where you can make your money. And then on the gamma scale, even a shorter time frame where you're looking at thunderstorms. And again, thunderstorms will change the environment, but these are kind of the two major areas that can be very effective in mesoscale analysis. And the predictability kind of increases from bottom up. It's pretty good. The models are pretty good at forecasting convective mode on a meso alpha scale, and it's good a lot of times with being able to predict convective mode changes on the beta scale, but not perfect. It's not going to be able to tell you exactly, for example, if you're going to have a QLCS structure. So that's where you have to apply really good mesoanalysis to be able to correctly anticipate hazard potential. So how do you maximize the effects of good mesoanalysis to decision making? Well, I think it's important to focus on problem solving and decision making. There is a distinction. Problem solving is 9/10 capturing and learning repeatable actions, and decision making, on the other hand, is for that rare breed of a decision making where the decision has not been made by someone with experience and authority. So that's the silver line. That's the commonality to every problem: deciding what the problem is and be able to weigh the pros and cons and be able to know what the repeatable solutions are. So good decision is about being able to predict likely outcomes and being able to see the connections between cause and effect. Not everyone's going to have this. So a kid goes through the line, for example, and asks his dad, well, did I like this? Here's some potato salad. The person doesn't know. So the dad turns to her and says, "You've had potato salad before." The girl says, "Well, I know, but did I like them?" So that's the thing. Experience alone is not enough for good decision making. You have to be able to capture and learn repeatable solutions and know what happened So the key to learning from experience is paying close attention and aggressively drawing lessons from one's experiences. If you begin to see the patterns in causes and effects, such as increasing in low-level wind shear, you can start to think ahead with insight and be able to anticipate potential development with severe weather and effective warnings. That's the key to decision making and how you maximize the effects of good mesoanalysis in the process. So the very last case is kind of another problematic. You've got a person at the mesodesk. Wait, there's no one at the mesodesk. That's part of the problem. We oftentimes do not staff the meso because they get taken up by other duties. So we've got to figure out how to make sure that person is dedicated and doing the job. And so what I want you to do, follow up on this activity, is send a summary of the specific job duties in your office, how you accommodate this, describe what and how things are done, what tools you look at, and then describe how you'll be proficient and be able to commit yourself to learn how to do it, because that's key. Send the summary duties to me at this address, and we'll make sure that you get credit for this webinar. And we thank you for your time and attention today.